Good morning and welcome. My name is Robbert Dijkgraaf. I'm the director and Leon Levy Professor here at the Institute for Advanced Study in Princeton. It's a cold and wintry morning here, and I'm happy to, in this live session, to answer some of the questions you had been asking related to my lecture about the past and future of unification in the masterclass I've given for the World Science University. And perhaps you might be interested that this session I'm doing from kind of historical grounds. The Institute for Advanced Studies, of course, many famous physicists associated to it. One of was the long-term director, J. Robert Oppenheimer, and in fact, we're sitting now in his old office, and I want to start by showing you this slide, which is a slide where you actually see a picture of there we go, of him sitting in his office surrounded with young students. So this is a picture from 1948 and discussing the latest things in physics, particle physics, and unification. And in some sense, what we are doing now is a zooming back from 1948 to 2015 and do it in a different fashion from the same office, but now with using our digital means to have a discussion. So I want to start with the first question. It's actually a question asked by Christopher, who said, you talked about Wheeler's one electron universe idea and how it helped Feynman develop Feynman diagrams. Are antiparticles understood to be particles traveling backward through time, or are they totally different? So perhaps I can start by kind of briefly recapping what I said at the lecture, which is that we should think of a particle as moving in space and time, so it moves upward in time. But then Wheeler asked the question, suppose the particle can go up and down and up and down and up and down and weaves this big knot in space-time. Then we can look at it at several moments. At the first moment, we slice space with a time slice, we see a single electron. But if we slice it in the middle, we see many particles sticking in and out, coming up in time and down in time. And his theory was that the particles going up in time are the electrons, indicated here with a minus sign, and the particles going down are positrons or anti-electrons. And a positron going up in time should be the same thing as an electron going down in time. So the question was, is this just a nice metaphor, or is this actually what's happening? And the great thing is that this is exactly what's happening. In fact, it's a great feature of our understanding of particle physics that we can draw these famous Feynman diagrams, and here you have an example of such a diagram. We can draw these diagrams, and by orienting them differently in space and time, they're describing different processes, but they are computing them in a uniform way. So the rules of quantum field theory, the rules of particle physics, are extremely powerful because they take full advantage of the symmetries of space and time. And let me explain this with some simple facts. So here we have a basic building block of, for instance, the theory of quantum electrodynamics, which is the theory of matter, in particular electrons, interacting with light. It's the theory that Feynman and others got so famous for. And so this process that I've drawn here, which at this moment looks like a particle going up in time and then emitting something, a photon, actually has many interpretations. And let me just go over the various interpretations. So for instance, here's my first picture. Are oriented as such that you could see this as an electron going up. If you can follow my cursor, it go up. And at this point it reflects because it shoots out a gamma, which is a photon, a light particle. So here this diagram is representing the emission of a photon by a accelerating or changing electron. This is, of course, what happens if we switch on a light bulb or if electrons go around a particle collider and they radiate, so-called synchrotron radiation. Whenever an electric charge changes course, it will actually emit electromagnetic radiation. This is this diagram describing this. Now the same diagram can also be oriented like this. And now it describes something completely different, because now it describes a photon being absorbed by an electron. Of course, this has happened when we see light and light falls in our eye, and it makes a reaction, it triggers a chemical reaction because a photon is absorbed by an electron in one of the atoms in our retina. But I can do more. For instance, I can orient it like this, and now this is an example where now the electron is going backward in time, and you could say it's the time reversal of a emission. So now it's an anti-electron or a positron absorbing again a photon. And this is again a process that can happen. And there are many other variations. Here's another one. Now I oriented the diagram that the photon is coming in. So what does this describe? It describes a photon. At some point, it's going up in time. At some point, it decays into two particles. And now we would see this as an electron on the right-hand side and a positron on the left-hand side. So this is the process of particle creation, of particle-antiparticle creation, through a very intense, for instance, intense gamma ray or very intense electromagnetic field. And this is something, again, we see often in particle accelerators. A very high intensity photon will be emitted, and it can then decay in this way. This is the opposite. Again, still the same diagram, but now oriented such that we actually see the reverse. This is a process where a particle and an antiparticle annihilate, and they create a photon. So that's the process where particles can disappear in pairs, a particle and an antiparticle. And then matter is transformed into radiation. And this is basically one of the incarnations of E equals mc squared. It's mass being then transported into energy. So for instance, if we go back to the original diagram, the famous Feynman diagram, then the rules of quantum field theory are such that we have different interpretations of this single diagram. And by allowing particles, depending on whether they forward or backward in time, to be interpreted as particles or antiparticles, we have great flexibility. So here, for instance, is a diagram that describes an electron on the left-hand side and a muon, actually an anti-muon, on the right-hand side. And so it's an electron going up, or a muon going down, or an anti-muon going up in time. And what happens is that one of the particles, say the electron, will emit a photon, and then it's absorbed by the other one. So this is the process where particles interact by exchanging force-carrying bosons. In this case, since it's electromagnetic force, it's photons. And in this case, it will be a negatively charged and a positively charged particle. So this will be an attractive force, the attraction between negative and positive charges. But the same diagram can again be reoriented. And if we orient it like this, you see that the same diagram describes a completely different process. It's now an electron and an anti-electron annihilating, creating this photon, that then the photon creates again another pair of particles. In this case, a muon and an anti-muon. And the important thing to stress here is that the diagram by itself has a unique expression in terms of a mathematical formula that computes the rate that this particular quantum mechanical process can appear. And since we can orient the diagram in so many different ways in space-time, it tells us something extremely powerful. It tells us that all these different processes that on the one hand might be completely different, like particles annihilating and being created again, or particles being deflected through electromagnetic force, that are all basically equal. They're all unified. It's a unification of processes in terms of a single diagram. And that's what made Feynman's discovery of Feynman diagrams so powerful because the single diagram captured a whole bunch of different physical processes. Now, this question automatically kind of feeds into another question, actually a question that Julius asked. He said, you mentioned the Casimir effect that's caused by virtual particles. In what way does the uncertainty principle give rise to the existence of virtual particles? And how do we distinguish it from other forces? And this goes exactly in the heart of diagrams like this. So I described the diagram like this, or the previous one, this one, as the exchange of the electromagnetic force through a photon. A photon that's emitted by one charged particle and then is absorbed by another one. Now, you might ask, wait a moment, if I put two electric charges, I feel the electromagnetic force, but I don't see photons, I don't see light particles being emitted. And that's true, because these particles, for instance, this particle that sits in the middle over here, or the same particle that sits in the middle over here, they're not physical particles. They're not particles which are associated on shell. It's not particles that satisfy the equations of motions of particle physics. So, in many ways, the particles are mathematical objects. These diagrams are mathematical objects that allow us to reconstruct physical effects, like the creation of particles or the deflection of particles, in terms of intermediate processes. And these intermediate processes play an important role. If we go back to the original question, this was my image that I had about how to think about dark energy, about the vacuum energy, about the energy present in the vacuum state, which is by definition the state that has no particles. That there is this kind of creation of particle and antiparticles, which are in some sense allowed using the rules of quantum mechanics. And we gave this description in terms of a process in space-time. It's a particle going up and down in time, or in terms of a Feynman diagram, it's the process like this, which we can think of as an electron going up and going down, or you can see it as the creation of an electron and anti-electron out of nothing, and then being annihilated again. Well, indeed, if you look at this particular process, you might say, how is this possible? How can we create out of nothing, at the lowest state of energy, a particle and antiparticle? Because what happens to conservation of energy? Well, the only way to do this is to associate positive energy to one particle and negative energy to the other particle. But we know that particles don't have negative energy. They don't have kind of a negative mass. Even an antiparticle still has a positive energy. So processes like this, they describe particles, but they're not particles that can be measured. It's particles that can only live within the formulas and pictures that we draw. So it's very important to distinguish that, if you think about the rules of quantum field theory, about particle physics, about the pictures that we are drawing, that we should make a distinction between two kinds of particles. There are the real particles, the particles that we can measure, that say click in a detector, that satisfy the equations of motion, that is, their mass and momentum and energy are related. And then there's a different kind of particle which lives as an intermediate state, and it's not a physical particle. It can violate many physical laws. That, for instance, its energy and its momentum and its mass are not related in the usual way, but they are extremely useful construct to describe the laws of physics. So, for instance, if you here you have a much more complicated example of a Feynman diagram that describes the reflection of one electron by another electron. So it's the repulsive electromagnetic force. If you think about it, it's quite complicated. We see on the top, we see a photon being exchanged. On the bottom, another photon is exchanged. But the photon, for a brief moment, creates an electron-anti-electron pair. Then it combines again, the pair and anti-pair. The pair combines again to form a photon that then continues and is absorbed here. Now, in this picture, there are many particles floating around, but there are only 4 of them. The two incoming electrons and the 2 outgoing electrons which are real particles. So these are particles that we could detect in our colliders. These are particles that we could measure. All the other particles here are actually examples of virtual particles. So they describe in an important way the interaction. And the great thing is it organizes the interactions in a good way, because if you have more and more of these virtual particles, that the diagram becomes more and more complicated, like a diagram like this, then actually in a good theory that has a perturbative approach, the contributions of these complicated diagrams will be smaller than the leading diagrams. So again, this is an example, a very complicated example of an electron just going through, creating a whole cloud of virtual particles. It's only the incoming electron here on the left and the outgoing going on the right that are physical. All the ones in between are unphysical quantities. And here we have to discuss, this is something which is allowed in quantum mechanics. It's perhaps wrong to call this the uncertainty principle. I mean, the uncertainty principle of particles is that you don't know of a particle at the same time where it is and what it's moving. You don't know what its position and its momentum space is. So you can label particles only with one of the two numbers, either with its momentum or with its position. This is in some sense a different kind of uncertainty principle, because this is an uncertainty principle of fields. It just tells you that the fields themselves, the fields that give rise to the particles, they are quantum mechanical objects. And so there are natural fluctuations in these fields. And the fluctuations in the fields can be described in terms of the virtual particles. So I think that's an important distinction. And if you want to have a mental image of what a quantum field theory is, you could think of it, it's a combination of the real particles, which is the classical description, and on top of that, there is this cloud of virtual particles that capture the quantum mechanical nature of quantum field theory. So this is what I wanted to say about this extremely important fact of particles and going back in time. It's a terrific idea, and it's fully functioning. It's not a metaphor. It's exactly how quantum field theory works. And it's a very powerful unifying principle that it brings many, many different physical phenomena all together into one concrete physical mathematical formula, mathematical picture even. Now, I want to go to another bunch of questions which are related to the fact, how can we think about string theory as a theory of gravity and quantum gravity? And so I want to go back and perhaps again make a slightly different approach to how to think about string theory, which is more historic. So actually I want to start with electromagnetism. So there are two ways to think of electromagnetism. It is the way in which you can think in terms of the field, but there's also another way. So basically, here you have a picture of an electromagnetic field outside a charged particle, and this we have seen, it's the lines, the flux lines of the field. And in general, we think of these electromagnetic fields, that's part of electromagnetism. They can penetrate everything, they spread around space. If you think not in terms of the field, but just the flux lines, so basically going from Maxwell back to Faraday, then actually it's a very useful way to think about fields, because other things can happen. For instance, in the strong force in quantum chromodynamics, the electric field is confined. It cannot spread all over. Basically, the flux lines glue together, and they form tubes. This is something we see in experiments. And this is the modern way of thinking about the origin of string theory. String theory started describing the strong force, but basically describing now, would we say, these flux tubes. And these flux tubes can be connecting, for instance, two quarks, a quark and antiquark, which would be an image of an open string, but they can also be glued together, and you can have a closed string, which in the language of QCD, of the strong force, we would now refer to glue balls, something entirely made out of glue, out of the field, not about the particles. And these would be the closed strings. And so what happened in the string theory that we studied in the 1960s, early 70s, where string theory was applied to the strong force, we notice that if you look at the resonances here, you see all the various excitations in the string, that in particular there was a mode in the string which was massless, so it was a massless field, but it had the wrong spin. It had spin 2. And we know spin 2 is describing a force that is a force which carries a tensor character, and it's a spin 2, and there's only one spin 2 force that we know, and that's gravity. So then people kind of totally turn around string theory and said, wait a moment, this has and still has a very good application in understanding the strong nuclear force in quantum chromodynamics. But it also can be applied to the study of gravity, because string theory in the most natural way describes a quantum particle with spin 2, which we can identify as the graviton. So the spin 2 particle, we know there's one spin 2 particle around, which is should describe the quanta of the gravitational field. And that meant that string theory then had another life in terms of a theory of gravity. Now, it's important, I stressed this in my lecture, that the interactions in string theory are completely natural and follow from the geometry of the space-time pictures. In particle physics, we had Feynman diagrams describing the interaction of particles. Here, actually, we have world sheets, and these world sheets, as you see here, they are completely natural two-dimensional surfaces. There's no particular point I can indicate here where, so you could think of this again as a process where a string is going on the left, one is going on the right, and they exchange a force. There's an intermediate force, but you can't really indicate exactly where that particle is emitted. And for instance, for the electromagnetic force, we had an electron that was described emitting a photon and then absorbing a photon. Here it's only a string emitting a string and absorbing a string. It's all kind of unified in a very natural way. So string theory has the amazing quality that it unifies the matter particles and the forces that are being exchanged by force particles. So the matter particles and force particles are naturally sitting together. You can see this in this picture. And that means that, and this is not only true for simple diagrams like this, but also for complicated diagrams like this. So this is a loop diagram. And in fact, part of the ideas of Feynman diagrams now applied to string theory is that we have to sum over all these diagrams. So the important thing is that if one of these particles, one of these excitations of the string is describing the graviton, then the nature of these pictures here is describing that not only the particles, say the graviton, but also the interactions. So that's to say, string theory not only gives us a spin 2 particle, which we have identified as the graviton, it also tells us how the graviton interacts with everything else, in particular with itself. And we know the important point of gravity, it's an interacting theory. Gravity interacts with itself. That's why the universe expands. That's why we have black holes. That's why they're all kind of interesting gravitational effects. And all of that is captured by a formula, and that formula is Einstein's formula, of course. So here you see it. If you take Einstein gravity, which is very elegantly summarized in this formula over here, which is the Lagrangian for Einstein gravity, that the interactions that come out of string theory, if we go to the low energy limit, so we only look at the massless level, the string reduces in the basic level to the graviton, and the string interactions describe the self-interactions of the graviton. And the amazing thing is that you get this whole collection of interactions, because you can look at all the diagrams, reduce them to Feynman diagrams, and see what do you reconstruct in terms of theory of gravity. So you not get a theory of gravity, you get a very specific theory of gravity. And the amazing thing is that what you're getting is exactly Einstein gravity on the nose. If you truncate yourself to this massless level. And that's extremely powerful. And just to sketch how powerful it is. So again, so here I have an image. So this is a string moving in space-time. And now typically you would say, well, that's fine, but it's moving in a curved space. So here you see the curvature around. And we have to describe how the string is moving in this curved space. But now the essential element, basically the main conundrum to be solved, namely to unify general relativity and quantum mechanics, is say, wait a moment. General relativity describes classical space-time, but what happens if space-time is becoming quantum mechanical? How do we think about it? And how does the string that moves in this quantum mechanical space-time, how do we visualize this? And here again we can use the language of Feynman diagrams, because I would say this is a good picture to have in mind. This is kind of a cartoon impression of a quantum string. So it's not just a tube, it's a tube with many handles attached to it. It has a very complicated world sheet. It has many loops. And you can think of this just as an ordinary particle is surrounded by a cloud of these virtual particles that give its quantum mechanical properties. A string, or in its fundamental basic level, a graviton, is surrounded by this cloud of quantum mechanical objects around it. And so it's basically feeling and changing its own environment. It's influencing the space-time in which it's moving. And this is exactly what we want for a theory of gravity. Because in the theory of quantum gravity, space-time is not a static object. It's something that is being changed. It interacts. The background is interacting with the foreground. So in that sense, it's a very different picture. This is kind of a classical picture of a nice smooth background. Something is moving in that background, like an actor being put on the stage. This is the quantum mechanical picture, where in some sense the actor, by branching out through all these virtual clouds, is in fact forming and constructing the background. So in a very deep way, string theory is doing exactly what we expect of a theory of quantum gravity. It's making gravitation, it's making background, it's making space-time a dynamical object. Now, it's important to emphasize that this is actually more than just a theory of gravity. Of course, string theory describes attempts to describe everything in nature, because it unifies the concept of particles, forces, and particularly also the gravitational force. So all of these pictures, these string theory diagrams, like for instance this one over here, they can describe gravitons, but they can also describe other particles. And if you do more fancy string theory models, you will find models where you describe both the matter content that we know so well from the standard model, but also the forces in the standard model, like the electromagnetic force or the strong and weak nuclear forces. In fact, in these more complicated string models, and only spin 2 particles, there are spin 1 particles, there are spin 1/2 particles, which could be the electron or the quark. And so this is also a way in which string theory is really different from, for instance, a theory like loop quantum gravity or other attempt to quantize gravity. I think string theory is saying, well, there's only one way to quantize gravity. You can't just take gravity as a freestanding object and treat it quantum mechanically and then just add matter. According to the philosophy and the approach of string theory, gravity and matter and all the other forces are unified in a very, very deep way, because they all emanate from the same physical object. That is to say, from a string. Actually, I also want to say something about a question that was asked by Gordon about dimensions in string theory. Gordon asked, is it possible to have more than 11 dimensions in M theory or any version of string theory? Are we at all limited to a certain number of dimensions? And in fact, this is a question that, let me switch here, we should think about broader sense. So what do we mean by dimension? I would think, there's a kind of a way to think about dimensions that we do in everyday life, which are macroscopic dimensions. It's dimensions in which we can move and we can feel around. Now, the extra dimensions we have in string theory, well, clearly, there are only 3 space and 1 time dimension that we experience. So the extra dimensions in string theory have to be kind of hidden from us in some way. And that can happen in 2 ways. So there are basically 2 models here that we use. One is that they can be rolled up, as I described in my lecture. So dimensions can be very small. Another one could be that we are stuck to a kind of submanifold inside a larger dimensional space. Now, in the models in string theory where we have space-time dimensions which can be large, indeed it's true that in a perturbative string theory, the maximum amount of dimensions is total space-time dimensions is 10, and in M theory, with the theory of quantum supergravity, that can be extended to 11. But then you can ask, well, is there room for dimensions of another kind? And actually here there is at some point it becomes almost kind of very fuzzy, in the sense that, for instance, if you have supersymmetric theories, you can think of a superdimension as basically also by a different kind of dimension, but it's a dimension which is kind of infinitesimally small. If you have the so-called heterotic string, it has 10 large space-time dimensions, but it has 16 internal dimensions, 16 dimensions, where only certain modes of the string, the oscillations in the string that move to the left and to the right in the string, so one of these, say the right moving modes in the string, can explore these other 16 dimensions. And actually you can have more complicated string theory backgrounds where, from a certain perspective, you could think of it as moving in more dimensions than the 10 or 11 I just mentioned. But these dimensions are never of the kind that they can be grown large. So the important thing of the number 10 is that there are string backgrounds where we have, say, 10-dimensional Minkowski space. So all the space dimensions, all 9 space dimensions, and the added 10th time dimension can be made large, can be macroscopic. You can build a whole universe out of it. It's clearly not our universe, but it's a solution in string theory. Once you start rolling up dimensions to a quantum level, to kind of Planckian size, then the whole concept of a dimension, I would say, become less meaningful. So if you look in the string theory literature, you find models that are made, interacting models, that are based on spaces that have more dimensions. But for instance, even there, you could have 2 interpretations of that model, 2 different interpretations, where even the number of space-time dimensions, particularly the number of space dimension, is different. So my conclusion would be that the whole concept of a quantum dimensional space direction is kind of fuzzy, and so it doesn't really make sense anymore, and perhaps it's just not the most meaningful concept. We really are talking about quantum geometry, and quantum geometry is something where classical notions like dimension, length, topology no longer make sense. For the following question, I want to go to a question that was asked by video. So let me see whether I can open it up. And it's a question.
Hi, my question is in regards to the LHC finding the Higgs boson 2 years ago now. I haven't heard hardly anything about it since then, and I'm wondering what's going on. And, quite frankly, what's the next step? Is the LHC done with? What can we look forward to seeing in the future on that front?
So that's a terrific question, and it's very relevant these days, because the LHC had a successful run. You all know it ran not at the designed energy, because there was a small mishap at the beginning, and they had to be careful. It was a great success because the Higgs particle was found. But we're now all readying for the next run, which actually will start at the beginning of June of this year. And it will run at much higher energy. We hope around 14 TeV. And and so now the real work begins, because I think, we were all very, very happy that the Higgs particle was found, but it was, in some sense, predicted 50 years ago. Um, and it was long in the making. And I think we would all be seriously surprised if the Higgs particle would not have been found. Um, but of course, now the question really is what's next? And it's important to stress that we have this beautiful standard model, including the Higgs particle, but the standard model is internally inconsistent. It will not survive. If the standard model, as we know it right now, will make the whole universe unstable and the universe will collapse, and it clearly doesn't. It has been around for 14 billion years. So somehow the universe knows something that we do not know, and if our old kind of gut feeling is right, then we are strongly believing that part of the answer should be found in the next run. So what will happen is now that we'll have the LHC working at much higher intensity and energy. And one of my colleagues described it yesterday as follows. We have a race which starts with a sprint, a 6-month sprint, starting in June, so the second half of 2015, where we will very, very rapidly cover everything we have done before, then double the number of data. And if there's anything out there, like a new particle or a new force, something like we are hoping for, like supersymmetry, if it's out there, it should we should see some of it in so new particles should kind of announce themselves in the next half year, and after that the race turns, as my colleague said, into a marathon. Then we'll have another 2 or 3 years where we have to collect a lot of data, and we will look for other kind of phenomena that are statistically less likely to appear. We only looked at, in some sense, a small part of the standard model. We only looked at some of the simple processes which have a high probability of appearing. And but there are many other opportunities there. And the only way to find them out is to wait for a long time. And so that's something that we will start doing now, and we will be kind of mapping that out. So it means that you will also brace ourselves for a period where there will be many false alarms. That's the statistical nature of quantum mechanics. So we know even if there's something new out there, it will manifest itself only in a statistical fashion. So you have to gather a lot of data. There will be indications of particles which then will disappear. But we get an exciting 6-month, second half of 2015. And then we'll have to probably stick around for a longer few years to get the next round of measurements. Another question actually related to this is the question Colleen asked. She asked, do you think it's possible to find or create dark matter in the near future? If that happens, how would it affect our views of supersymmetry? Now, dark matter, the presence of dark matter, that's every day we get more and more astrophysical evidence that its presence is there throughout the universe in huge clouds around our galaxies. So the kind of indirect evidence of dark matter is mounting. The only way in which we can create dark matter in the lab, if we are lucky, we should be lucky in 2 ways. First of all, there should be a coupling between the dark matter particle and the particles of the standard model, because otherwise we won't be able to produce it by colliding the particles in the standard model. The second thing is that we have to be lucky that the energy of the lightest dark matter particle is such that it's in range of the LHC. Now, optimistic scenarios suggest that it is, and these optimistic scenarios have always been strongly connected to our models of supersymmetry, where in supersymmetric models, the so-called lightest stable supersymmetric particle, and it would be an excellent candidate for the dark matter particle. But we haven't seen any indications yet, so that makes people slightly worried. it's still an opportunity. As I said in my lecture, it's quite astonishing that the measurements we're doing, for instance, from the cosmic background radiation, the background that really are the oldest and the farthest object that we can study in astronomy, and the shortest distance measurements that we do at LHC, that they're both looking at the same kind of particle. And so there is a lot of opportunities there. I now want to move to a bunch of questions that were asked about the verifiability of string theory. Winona, for instance, asked, you said in class that it's much easier to disprove string theory than to prove one smoking gun to prove it correctly. What would be one of the ways to disprove it? And if new evidence arose that was contrary to string theory, what would be the next step? And this is also related to some other questions. For instance, people asked, can string theory tell us about the speed of light? Or that's a question of Tim. Or a question with Tremaine, how can we be sure that the laws of physics are evolving with time? And I think this boils down to some of what are the core elements of string theory. String theory is in some sense quite a conservative theory. It really combines quantum mechanics and relativity theory. So anything that we find that changes our interpretation and the rules of general relativity, for instance, the fact that the speed of light is constant, the fact that Lorentz invariance, the fact that you can basically orient yourself in any way in space and time. If we find violations of that effect, that actually will be not only a violation with general relativity or quantum mechanics, it will be a violation of string theory. Particularly also this is true for varying certain constants in nature. So there are some elements in string theory that are say kind of environmentally built because they are part of a certain compactification, and that compactification can evolve in time. There are scalar fields that do so, but there are other things that can definitely not evolve in time. And a lot of energy has been gone in cosmological observations and astrophysical observations to see whether fundamental constants, for instance, the fine structure constant that determines the strength of electromagnetism, whether it's if it has the same value now as it had, say, at the beginning of the universe. And we did find that it has remained constant in a very accurate way. And so I think it's more, it's some of these phenomena that would kind of disprove string theory. And I'd say there are many, for instance, other theories about quantum gravity that say that space-time is perhaps it's more like a lattice or something. So you cannot smoothly rotate. It should kind of be a discrete space. And I think if any indication of that would be in contrast with the fundamental principles of string theory. There are certain rules in quantum mechanics that essentially tells you that you can't have probabilities that are higher than 100%. If anything like that will be found, it will be in direct violation also of the principles of string theory. So there are, I think these are some of the easy ways to disprove it. I also want to relate that question to a question Luke asked actually, I think today. He asked, from a string theorist perspective, what are the greatest strengths of the theory and what are the greatest pitfall? And here we see, I think, and I think I emphasized this also in the lecture, the great strength is clearly its internal consistency. It's doing exactly what the doctor ordered. It combines the two great theories of quantum mechanics and relativity theory. And the fact that it can be done, and can be done in such an elegant way, in an internally consistent way, is an extremely powerful principle. And I think that clearly also has led to very interesting applications in a whole realm of sciences and mathematical fields. The pitfalls are clearly the fact that it's much less predictable than other models, where a model would clearly give a whole series of indications, would say, well, these and these particles are there, these are their interactions. And in string theory, part of that question is answered by asking how did the universe start? Like in string theory, some of the space-time dimensions have to be rolled up. Clearly, we don't see 10 dimensions; we see 4. Can be rolled up in many different ways, and this is the famous landscape problem. That instead of asking, giving a unique answer to the spectrum of particles and forces and interactions, it provides this menu with many opportunities. And at this moment, we don't have any good dynamical dynamical principles that select one background over another background. And this makes the theory extremely flexible, but people would say it's so flexible, it's hard to make it give a make or break prediction, which I think certainly being right in front of the second run of the LHC, you would love to say, well, you're going to find this particle at that energy with these properties. String theory at that point, it isn't that predictable, and that clearly I think is a great pitfall. And I think we should kind of always push the theory by making it kind of trying to find predictions that it can make. And personally, I see great hope in combining particle physics with cosmology, questions about the origin of the universe. I think we all feel that there are deep, outstanding philosophical problems there. What do we even mean by the evolution of the universe? How is that solution picked? And what happened exactly at these very early stages of the universe? And I think the string theory in a good position to answer some of these deep philosophical problems. I think it's important to stress over and over again that if you in physics there always have been two approaches. There's a bottom-up approach working with concrete measurements, the latest data, building out of the data. And then there is the top-down approach, thinking in terms of grand concepts. And in both cases, we have terrific examples. The particles have been discovered that nobody saw coming. And we have this terrific work of Einstein, basically having a grand vision of how space and time hang together, which turned out to be extremely predictive. This year, we're celebrating 100 years of the theory of general relativity. And look around, there's wonderful applications left and right. So we need a mixture of the two, and clearly, string theory is very strong in the top-down conceptual level. It's much weaker at the bottom-up level, and I think that's something that we all have to work with. I actually want to go to another question, which is a little bit about mathematics. Eric asked, how is it that mathematics, a human construct, is so true that it must be used not only to describe the universe, but even to understand it? And then you have a follow-up question, does it mean that more resources should be allotted to pure math research and development? And I must say, anybody working in this area, like me, we are continuously amazed about the power of mathematics. And my favorite phrase is this wonderful phrase by Eugene Wigner. He described it in a beautiful article called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And he illustrated with an example of the Gaussian distribution, which is everywhere in life. Everything is random distributions tend to be in Gaussian nature, and it's described by a simple formula. And that formula, it's quite amazing that if you look at the formula, I see it here on the screen. You see the letter pi, the Greek letter pi. So, in some sense, as you said, pi comes from the geometry of a circle. So in some sense, circles are everywhere where we see random Gaussian distributions. And there are so many examples of mathematics being powerfully applied to new directions. Galileo had this wonderful phrase, the book of nature, and I'm just putting a quote here where he says, philosophy is written in this grand book, I mean the universe, which stands continually open to our gaze, but it cannot be understood unless one first learns to comprehend the language and interpret the characters in which it's written. It's written in the language of mathematics, and its characters are triangles, circles, and other geometrical figures, without which it's humanly impossible to understand a single word of it. Without those, one is wandering in a dark labyrinth. And I think that's true now more than ever, that we have seen that mathematics is an extremely powerful way to describe the universe. And if you ask me, what is in essence a particle? What is an electron? It's very hard to beat the description as being a solution to the Dirac equation. It's a solution to a mathematical equation, and that's how powerful it is. And so the language of mathematics is extremely powerful. Let me just, I forgot that, so put it on the screen. Here is Galileo's quote, and it's Galileo's. I think was right, and I think many subsequent physicists have made the same point, and I think certainly also now. And so what we have seen is that math has been extremely powerful in guiding us forward. Einstein would not have been possible for him to do his work in general relativity if people like Riemann and others hadn't developed the language of abstract geometry in higher dimensional spaces that he could use. And but no, there are various points of view on this. For instance, now put this slide here. Now it's what's interesting that sometimes we see that there are two important elements driving us forward. It's the physical intuition, how quantum mechanics should work, how we think of particles, of forces, and then there's mathematical rigor. And I feel they're complementary. It's sometimes interesting that mathematical ideas that are phrased using physical intuition turn out to have to be proven in a way which are totally different from the physical intuition. So it's ideally you would like to combine the two, to have a deep intuition about the universe and make it all mathematically rigorous. But I think there might be complementary ways to look at the universe, and I think actually that's very powerful, because there is, for instance, string theory is wonderful that we have this great mathematician, but here you have Odysseus. He's tied to his ship because the sirens are trying to seduce him, and often people feel, well, physics is like this, being seduced by beautiful mathematics. Just the fact that the mathematics is beautiful doesn't necessarily mean that it's true, and so that's why I think we have always to be try to combine these two sides of our brain. The brain that part of our brain that has a deep physical intuition, and the part that wants to make it all crystal clear in a mathematical way. And it's the combination of the two, I think, actually, that's is so powerful, and that might be again the strengths and weaknesses of string theory. I want to perhaps take a few more questions that have been coming in during the lecture. Let's see. Jones asks, if a particle is traveling faster than the speed of light, does it mean it's going back in time? Could it mean a positron is an electron traveling faster than light? That actually is a very interesting question. Now, in some sense, you can think of indeed think of a particle, and I'm trying to illustrate it. So it would go up in time, like I hold my pen now, and in space-time diagram, if it goes faster and faster, it's starting to tilt and to tilt until it has 45 degrees, which means it's going at the speed of light. If you go even faster, it's moving basically almost in a flat direction, and then you could move further down till it's go back in time. Now, we have a good interpretation of going forward in time and going backward in time. One is particles, the other is antiparticles. if you have the intermediate part, which is going neither forward or backward, but basically more going in the spatial direction, it means that if 2 points in space-time are connected by a particle, so this would be true if a particle goes faster than the speed of light. It means that there is a way, an orient, you can, if you have 2 of these points, you can always pick a frame where these points are even, they are simultaneous, so they are, at equal time. So you can say it's connected instantaneously, and that means that it's no longer causally connected, because by flipping it slightly different, you can say, well, one is this point is influencing this, or if you rotate it differently, it's the other way around. So if a particle is moving faster than the speed of light, then actually it's no longer has, it can indeed go backward in time. It means that the beginning and the end is not clear which happened first. If you go even faster and faster, and you go even more backward in time until you're again going backward in time with a speed less than the speed of light, then again we have a good interpretation, because then it's an interpretation as an antiparticle. So the one-line summary is you cannot smoothly interpolate between going forward and backward in time. There's this intermediate area where you go neither forward nor backward, and that's the place where the tachyons, particle going faster than the speed of light, would reside. That's where we lose causality, and that's where we basically no longer think in terms of the usual cause and effect laws of physics, and so that's where we have to stop. Of course, the particles that we pictured in the virtual particles, the particles that we were picturing in my Feynman diagram. So if I go back to one of my favorite Feynman diagrams, let me just go out here and go here. So for instance, a diagram like this, if you look like at this virtual particle that's interchanged here, the photon that emits the electromagnetic force, that photon could easily and certainly at the way it's depicted now, it moves, it moves basically instantaneous. So it's in fact like moving much faster than the speed of light, although it's a light particle, amazingly, and that's because it's a virtual particle. So as a virtual particle, this photon in between, which can never be observed, actually is free to travel with any speed it wants to, but of course it won't be observed, and there's no way in which it can exchange information. It describes the force, but it cannot be used to emit information from one particle that then be absorbed by the other particle. Let's see, another question. Also an interesting question from AR. He or she asks, how does a particle acquire mass in string theory, and can it be interpreted in terms of the Higgs particle? Well, this is again a very good question. So if you think about the way, so there are two ways in which strings acquire mass. So the first one is actually pictured here. Oh no, let me just stop. We think of the string as a bunch of excitations, like pictured over here. So there are various excitations of the string. Let me put it on the screen, and you see the various excitations. And so you start with the ground tone, essentially, where this string is not fluctuating, and you have the higher fluctuations. These higher fluctuations are massive, but their masses come in order of essentially the string mass, which in many cases would be the Planck mass. So these would be gigantically heavy particles, masses of the order of a bacterium, not of an elementary particle. So this is the way in which the excited modes of the string become massive. In terms of the particles which describe, say, our low energy world, and which are the particles that we would use to describe the standard model, um, they would acquire their mass indeed according to the Higgs particle. And again, one way you can think about it is that the Higgs particle is kind of slowing down particles, or it's interacting with particles, because there's an interaction between any particle that carries the corresponding charge and the Higgs particle. So for instance, this string diagram, we could think of this left-hand side as being a string moving, and then on this kind of in-between element here, the string on which it's connected and which it's interacting with, could represent the Higgs particle. So in fact, the whole Higgs mechanism is in a very beautiful way incorporated in many models in string theory. And in fact, it even some of, for instance, the supersymmetric models, they're very beautiful because they describe, they unify the Higgs particle, which is a spin 0 boson, with the other bosons, the spin 1 boson, which is the electromagnetic and strong nuclear forces, so the W and Z boson and the gluons, and the spin 2 particle boson, which is the graviton. So they would all fit together in a very natural way. And I think, again, this shows the kind of strength of string theory. It shows two things. So, again, the beautiful mathematics of string theory. It shows it kind of hangs together in a good way, and it shows also that it's kind of conservative, because the way string theory is describing the properties of the standard model is really according to the laws of the standard model. So in that sense, it's very important also that we found the Higgs particle, because again, it's confirming in a very nice way what we knew, and it's in total coherence with our ideas from string theory. So I think I tried to cover as many of the questions that you asked. It's a great pleasure to interact with you here. Again, we are in a very kind of different world than we are in the days of Oppenheimer. For those of you who are turned in later, I end with this last slide, which is a picture of my office, but then in 1948, Robert Oppenheimer, the director at that time of the IES, talking to young students, and I feel that I was with you a little bit in the same spirit. So thank you very much for attending this live session.